Every major AI company is racing towards the same goal: build the biggest model, which includes more data, more GPUs, more money. But as a former product manager with Amazon, this is actually raising a couple of red flags for me. Because you see, you have to make decisions as a product manager, and some of those decisions include time, money, scalability, impact, and ROI. And that's just to name a few. So when I started digging into the math and the economics and the failure points behind the strategy of bigger is better when it comes to large language models, I kept running into the same problem. Scaling is hitting limits that no one can really ignore anymore. And I don't mean theoretical limits, because scaling is still working technically today, but it's running into brutal cost and infrastructure constraints. So when I mean limits, I mean hard limits, physical limits, financial limits, and most importantly, cognitive limits inside the models themselves. And one question kept bothering me while I was putting the story together. If bigger isn't the answer, then what is? Because the companies sprinting to scale up are now running into problems like GPU shortages, inference bottlenecks, energy consumption that actually rivals small cities, and training runs rumored to cost hundreds of millions of dollars. And even with all that, the models still aren't gaining human-level reasoning or understanding. According to Meta's chief AI scientist, Yann LeCun, one of the actual pioneers of modern deep learning, simply scaling models won't get us to the real intelligence. He argues we're missing entire pieces of the puzzle. So if the same researchers who helped build the industry are now questioning the strategy behind it, where does that leave us? So today, I want to walk you through what scaling actually gave us, where it's failing now, and the 5 alternative paths that researchers and engineers are quietly trying to explore behind the scenes. Because the next breakthrough in AI may not actually come from making something bigger, it may come from making something different. But let's start with what scaling actually did and what it never actually solved. Before we can talk about where scaling breaks, we really need to understand what scaling actually did. When researchers discovered that language models improved simply by making them larger, it looked like a cheat code. Add more data, add more layers, and more compute. Performance goes up. Makes sense, right? And for a while, it actually worked beautifully. According to the original scaling law research from companies like OpenAI and DeepMind, model performance followed a remarkably smooth curve. Bigger models made fewer mistakes, learned faster, and generalized better. The curve held long enough that the bigger, better model started looking like less of a strategy and more like a law of nature. And that's why we saw the leap from GPT-2 to GPT-3. That's why every major lab, OpenAI, Anthropic, Google, Meta, followed the same recipe. And to be fair, scaling actually delivered real capabilities. Models actually became fluent, they became useful, they became powerful enough to help people do things like write code and reason through tasks, and even navigate complex information. So in short, scaling gave us the modern AI boom. But here's the part most people never actually hear. Scaling also exposed the limits, because as the models got bigger, the cracks got more clear. Large models really struggle with cause and effect, and they fail at planning more than a few steps ahead. And, as we all know, they can hallucinate, sometimes more confidently than smaller models. So even when accuracy improves statistically, grounded reasoning does not improve at that same rate. And once you see that pattern, better numbers, same cognitive flaws, that illusion breaks. Scaling improves pattern recognition. It does almost nothing for understanding. It's like measuring every grain of sand on a beach and still have no idea how a coastline actually forms. And that's where the curve actually begins to flatten. And it's not because the models are bad, but because the architecture has limits in reasoning, limits in abstraction, limits in memory, and limits in real-world modeling. The model gets twice as large, but only a little bit better. The compute cost in this almost double, but the intelligence barely moves. And in some benchmarks, larger models even regress a little bit. They become overconfident in answers. that are statistically plausible, but actually incorrect. Bigger isn't always smarter. And when you combine that with the cost curve, which is rising exponentially, you get something a little alarming. AI progress is being built on a method that delivers less and less value for more and more money. And that's the first real breaking point, because if scaling no longer guarantees improvement, how do you justify models that cost hundreds of millions of dollars to train? To answer that, we have to look at the economics and the crisis inside the industry that almost no one is talking about. Once the scaling curve started flattening, something else started rising. It's the cost to keep this entire system alive. And this is where my research took a little bit of a turn, because the numbers aren't just big, they're unsustainable. Let's start with the economics. According to multiple independent analysis, training a frontier-level model today can cost hundreds of millions of dollars, and not just to build, but to update, maintain, and serve at a global scale. And that's just one model. Labs like OpenAI, Google, Meta, and Anthropic, the big four, aren't training single models anymore. They're training entire families of models. Each iteration is bigger, each iteration is more expensive, and each iteration is also consuming more and more hardware, which kind of raises one simple question. What happens when costs grow faster than intelligence? Because that's exactly what's happening right now. The economics are starting to invert. Scaling no longer guarantees breakthroughs, but it still guarantees the bill. Now let's go deeper, beyond money and into physics. Today's frontier models require thousands and thousands of high-end GPUs basically running in parallel. These clusters draw enormous amount of power, and they generate a large amount of heat and strain on local electrical grids. And they do this in ways that data centers weren't actually designed to really ever handle. And the GPU shortage, it isn't hype. It's a real bottleneck. Companies are competing for the same limited supply of chips. Even organizations with deep pockets are running into availability ceilings. They also run into deployment delays and rationed access and throttled inference capacity. But here's the part that no one actually acknowledges. Even if you solved the money and you solved the hardware, you still run into the architectural limits. Scaling a transformer doesn't magically grant it memory, reasoning, planning, or cause and effect in understanding. The bigger these models get, they actually hallucinate more confidently. They approximate more aggressively. They become harder to interpret. They require more safety layers just to remain reliable. So in other words, bigger reduces some errors, but leaves core reasoning gaps mostly intact. And that is the breaking point the industry doesn't want to talk about. Because we built a strategy where the cost is exponential and the returns are incremental. So I started asking the obvious question. So if scaling is becoming too expensive to continue, too physically constrained to expand, and too cognitively limited to evolve, then what actually comes next? Because if the current approach can't deliver real intelligence or even sustain itself long term, then the next decade of AI won't be defined by size. It'll be defined by architecture that replaces it. So let's talk about the 5 paths that AI can actually take next. So we have path number 1, which is scaling, and right now that's the dominant strategy today. This is the strategy that built GPT-4, Claude, Gemini, Llama, and virtually every frontier model of the last 5 years. And the idea behind it is brutally simple. If you take a transformer and make it bigger with more parameters, more data, more compute, its abilities keep improving. And for a long time, this held so consistently that the researchers began speaking about it almost as a natural law. Scaling unlocked the jump from cute toy chatbot to something that can actually summarize legal documents. It could write software. It could actually pass professional exams. It could break down complex systems and generate content that looks effortless. But scaling comes with realities most people actually never see. Because first, the cost curve is brutal. Running a frontier model requires huge GPU clusters, massive energy draws, and dedicated cooling systems, and billions of dollars of ongoing operational expense. And only a handful of companies on Earth can even really afford this race. Second, scaling is actually hitting a physical limit. GPUs are now bottlenecked by things like memory bandwidth, interconnect speeds, and power availability, not to mention chip yields and even data center floor space. The third thing with this is bigger doesn't always mean better. Past a certain point, adding parameters gives diminishing returns. DeepMind's chinchilla study showed that more data often beats more model. And fourth, scaling doesn't fix forgetfulness. A trillion parameter transformer still has no persistent memory. Every conversation starts from zero, and scaling doesn't really do anything to solve that. And fifth, scaling centralizes power, which we'll definitely talk more about later, but if only a tiny set of corporations can afford the largest models, everyone else is forced to rent intelligence from them. And this is where the debate splits. Meta's top AI leadership, including Jan LeCun, argue that scaling is impressive but fundamentally incomplete. It's useful, transformative, definitely, but not sustainable as the primary engine of progress because scaling is a straight line that eventually will hit a wall. Now, if path 1 is all about make the brain bigger, then path 2 takes a different angle. Don't make the model smarter, give it more ways to interact with the world. And this path actually has 3 pillars: multimodality, tool use, and agents. Individually, they are very useful. Together, they form a strategy that actually tries to sidestep the limits of scaling by making the model extendable, not enormous. Now, with multimodal, the system learns to see, hear, and read. A multimodal model doesn't rely on text alone. It can process images and audio and video and chats and charts and PDFs and documents, even screen states. This turns the system into a kind of universal input engine. The real world isn't a text file, it's a visual, auditory, spatial experience, right? Once a model can see and hear, it can solve problems that were previously impossible for text-only systems. But let's be clear, multimodal isn't intelligence. It's basically bandwidth. It widens the doorway the model looks through. It doesn't improve how the model thinks. As far as the tool use, the model doesn't think harder, it basically delegates. And another piece of path 2 is the tool use. Instead of forcing the model to think everything through internally, we allow it to reach outward, doing things like searching the web, running code, or query an API. Anthropic is using it to analyze spreadsheets or retrieve documents, execute scripts. And this is why modern models seem so much more capable than GPT-3. And it's not because the model became a genius, but because it learned how to use external tools. And in practical terms, this turns an LLM into a digital Swiss Army knife. But again, tool use isn't capability, not cognition. It's like giving someone a calculator. They still need to understand why they're using it. And agents, the model doesn't just respond, it acts. Agents are the natural evolution of tool use, because an agent can do things like break a task into steps, choose which tools to use, it can monitor progress, recover from errors, and sometimes run autonomously. Think of it as workflow automation powered by language models. Not intelligence, not autonomy, just a structural execution. Agents are great for things like research, debugging, scheduling, data cleanup, and even multi-step planning. But they still inherit the limits of the underlying model because they forget, they hallucinate, they get stuck in loops, and they need supervision. They drift without the guardrails. So path 2 increases what AI can do, but not what AI can actually understand. So let's talk about path 3, which is the memory-centric architecture. Now, path 3 is quieter than scaling and less flashy than multimodality, but it might be the most important shift in the entire field. It starts with this simple idea. Stop trying to make the model bigger. Start making the memory smarter. Now, right now, most AI systems behave like a brilliant student who takes beautiful notes and then throws the notebook away at the end of the conversation. Every session starts from zero, every task resets, every insight evaporates. This is one of the main reasons companies keep scaling up their models. If the model can't remember, you have to stuff everything into its parameters, and as soon as the window closes, all context basically disappears. A memory-centric architecture flips this logic completely. Instead of forcing the model to store the entire universe in its weights, you separate the system into two components. You have the model does the reasoning and the memory holds the knowledge. A system like this has three parts. One part of it is smaller, faster. It's a reasoning model. It focuses on language, logic, and problem solving. It's not an encyclopedia for memory. Because part two is long-term memory layers. Not personalization, not conversation history, but actual persistent knowledge, documents, corrections, previous work, project history. And number three, a retrieval mechanism. When you ask a question, the system pulls only from the relevant pieces forward because you could stop discarding the information you've already paid to compute. And just to clean up the confusion, because even I had questions on this, a memory-centric system is not like ChatGPT memory because that stores preferences, not knowledge. And it also is not custom GPTs. Those are the static instructions that we get basically as a file pouch. And I know GPT also runs projects. That's user-organized workspaces, not autonomous memory. Autonomous memory, probably a better way to say it. It's also not a RAG retrieval augmented generation system because that retrieves documents you upload. It doesn't decide what to remember. Now, in practice, early memory-centric systems will probably look like RAG systems or supercharged RAG systems with long context and logging, not something completely alien. A true memory-centric architecture, though, doesn't wait for you to upload a PDF. It doesn't reset when you close the tab, and it doesn't pretend to learn your personality. It simply stores what is useful, it organizes it, and retrieves it later. It's kind of like a researcher building an archive over years instead of rewriting the same notebook every morning. But let's talk about path 4, which is the world models and predictive systems. Because if path 1 is making the brain bigger and path 2 gives the brain more tools, then path 4 is something altogether very different. Because it's not about scale or bandwidth or delegation, it's about giving AI something it has never truly had. A grounded understanding of how the world works. And this direction is called world modeling. And it's one of the most active areas of research inside DeepMind and FAIR and the robotics and self-driving industries. So what is a world model? Well, simply put, a world model doesn't try to predict the next word. It tries to predict the next state, the next frame of a video, the next position of an object, the next outcome of an action. It tries to predict how a system changes over time. It learns the structure of reality and not the structure of a text. And this is how self-driving cars actually anticipate road conditions, how drones navigate unseen environments, how robots learn to grasp objects they've never touched before. A world model is less like a chatbot and more like a simulator. And why does this path actually exist? Simply put, large language models have a fundamental weakness, and it's something that scaling basically can't fix. They don't really understand cause and effect. They don't understand physics. They don't understand constraints. Gravity doesn't just turn off because you phrase it eloquently in a prompt. An LLM is a pattern engine, and a world model is a predictive engine, are fundamentally different things. And right now, to be clear, just to put this out there, world models are strongest in constrained domains like robotics and simulation, but turning them into a general reasoning tool is still very much an open research problem. So it begs the question, why does predictive intelligence actually matter? When an AI sees a cup sliding toward the edge of a table and predicts it will fall and shatter, that's not being smart. It has internalized object permanence, the continuity, the physics, and the consequences. Now, human beings actually develop this intuitively over time, and AI doesn't do that, unless you force it to learn from the world instead of forcing it to learn from language. Now, imagine giving that predictive ability to a language model. Suddenly, things like planning become possible, not by guessing, but really by simulating. And this is why Yann LeCun argues so strongly that LLMs lack essential components for true intelligence. They learn how language works, not how the world works. Now, just to be clear, LeCun's position is one of several competing visions. Some labs like OpenAI and Anthropic still believe scaling transformers, augmented with tools, and memory and better training will actually carry us much further. And others like Meta are betting on new architectures entirely. And so you may be asking yourself, why this path matters for the future of AI? Because language models are great improvisers. World models are great predictors. And the future likely needs both. Because modern AI doesn't understand anything. It stitches these patterns together. But a world model gives it the missing piece, the dynamics. A language model can tell you how to describe a bridge, but a world model can tell you whether the bridge falls when you actually test it. Those are wildly different capabilities, and only one of them leads to real reasoning. But that brings us to path number 5, because this one's a little bit different. There's one path that researchers are taking seriously, but still in the minority and speculative. Just want to put that out there. This path is actually built on a class of models called diffusion models. The systems behind things like Stable Diffusion, Midjourney, Runway, Pika, and much of the generative video explosion. Now, at first, diffusion looks like a clever way just to generate images. But under the hood, diffusion does something far more interesting. It reasons by refinement, not by prediction. Diffusion doesn't guess, it iterates. Transformers try to predict the next token in one shot. It's a fast sprint, it's a high stakes. If it gets it wrong, the whole chain collapses. But diffusion works differently. It starts with the noise and improves the signal step by step, gradually converging on a coherent result. This is closer to problem solving than prediction. You start uncertain, you refine the data, you check it, you improve it, and then repeat. And that iterative loop makes diffusion naturally stable and naturally controllable. Two things transformers actually struggle with as they get larger. This is why Stable Diffusion's founder, Imad Mustaq, keeps arguing that the true frontier is not mega transformers, it's the evolution of diffusion in general purpose architecture. And you don't have to agree. There's still a lot of testing that needs to be done on this, but the argument is real and happening inside labs. And in case any of that's confusing, let me just run through the clean explanation for you guys. Transformers predict the next piece. Diffusion starts uncertain and then refines until it corrects. One is a guess, the other is a process. And if the transformer scaling curve is flattening, then diffusion may be the off-ramp the field pivots towards. So why does any of this matter to you? Why does this matter to society in general? When people talk about the future of AI, the conversation usually stays inside a box. You'll have questions like, what's the next model? Or how smart is it going to be? Will it replace my job? We've all had those questions, but the real story isn't just about models. It's about infrastructure, power, and who controls the actual intelligence itself. Because the moment AI stopped being a novelty and started becoming an infrastructure, the stakes in all this changed. This isn't a software race anymore. It's actually a huge economic shift, a geopolitical shift, a societal realignment, if you will. And the consequences to all of this are already visible. Now, in my opinion, compute is becoming the new oil. And I know it's not the perfect analogy because unlike oil, compute efficiency actually improves and hardware generations turn over. But in terms of the leverage and dependency, the comparison is really hard to ignore. Governments are securing GPU supply chains the way they once secured petroleum. Corporations are actually signing multi-year energy contracts just to guarantee model training. And data centers everywhere that they're trying to launch are actually triggering political fights over land, water, and electricity. When compute becomes a scarce national resource, AI stops being tech and it becomes leverage. Then we run into the centralization problem. What happens when intelligence gets centralized the way that banking did? If only 4 US companies and 2 Chinese state labs can afford trillion-dollar parameter models, the future doesn't look democratized, it looks gatekept. A world where intelligence is rented and not owned, where it's accessed and not actually possessed, where it could be metered and not autonomous. This is why smaller, modular, memory-centric, and diffusion-based models matter, because they enable distributed intelligence, a world where AI runs locally, at the edge, and even offline. This is fundamentally different from a world where every query requires permission from a remote supercomputer. One future is dependent and the other is sovereign. I'm sure some of you have heard of these arguments. The global division is actually about to widen because countries outside the US and China access are already worried that they'll be locked out of competitive models. And some nations are actually building national LLMs, not out of pride, but out of fear. Fear that a handful of corporations could control language, knowledge, and information flow. And they could do this in the same way colonial powers once controlled trade routes. Now, if decentralized models win, you get small, efficient, memory-enabled or diffusion-based systems. You get almost a second internet. Intelligence as an exportable good, not a centralized dependency. But on the other hand, if the frontier AI remains purely bigger is better, the rest of the world basically becomes an API customer service department. And that leads us to the human consequence: trust. And here's where most people will feel this, but probably is rarely articulated. What happens to trust when every interaction is mediated by systems that we don't understand? And I'm not talking about hallucinations, because those actually will decrease as architecture evolves. I mean something just a little bit deeper. Who actually decides what the model refuses to answer? Who sets boundaries of basically what's acceptable and what knowledge is? Who decides what gets amplified and what disappears? And this is why smaller, interpretable models actually matter. When AI becomes a tool, not an oracle, the power dynamic changes. You get autonomy instead of dependency, transparency instead of decree. You get agency instead of blind trust. A world where intelligence is personal, not broadcast. So which future we actually get depends entirely on which architecture wins. And it's not just technically, but politically. And this is why the Meta chief scientist isn't debating parameter counts. He's debating the future of governance without calling it that. The architecture shapes the incentives shape society, and society shapes the decades that actually follow. So in the end, the future won't be bigger, it'll just be different. You've been fed a very specific story. The models get bigger, the numbers get larger, the charts move upward, and somewhere at the end of that curve, intelligence shows up. But after looking at the data, the architectures, the economics and physical limits, the energy demands for that matter, and even the supply chain constraints and the geopolitical landscape, the truth is almost embarrassingly simple. The next era of AI won't be won by size, it's gonna be won by structure. Because I don't believe scaling is gonna get us there. The point is that the frontier is shifting, so if you're trying to see where this all goes next, don't look at parameter counts or leadership boards, don't look at who stacked the most GPUs, look at the researchers asking the stranger questions. Things like, what is understanding? What should a model forget? And how do you build intelligence that reasons and not recites? And also, what shape should intelligence take in the first place? That's where the real breakthrough is actually going to come from. Not from another trillion parameter system, but from a fundamentally different way of thinking. I hope you enjoyed this episode of The Archive. Thanks for tuning in, everybody. See you on the next episode of The Archive.